Just some main things. We talked about sending charged particles through magnetic fields and what happens to those, and oh, sure enough, there's a force. And for those that have done the lab that dealt with this one, we'll talk about that here in a second. I will take a step back and say there's a force there. I can even do this and say that's a magnetic force. But always remember that's the force of what on what. So what's that they force on? And then who's doing the forcing? Man, this board writes nice. In case you all haven't noticed, they put the new board up over spring break. All right, what direction is the magnetic field? Send that particle flying in there. This is the force on what? On the moving charged particle. Who's doing the forcing? So the magnetic field is going to push on that charged particle. This is how strong that force is going to be. So again, it depends on what kind of charges you send in there, how fast is it going, how strong is the magnetic field. What's this part deal with? That's the orientation between really these two things. The direction that your particle is moving and the direction of that magnetic field. So you got two things there with directions. That's the angle between those. If they happen to be perpendicular, like in this case here, then theta is 90 degrees, sine theta is 1, so that part looks like it disappears. But if they're not completely perpendicular, then do watch that. We have to deal with that sine theta part. So that's how strong that force is going to be, and how do I know which way that's going to get deflected as it flies through that particular example. So that's one of our right-hand rules. And remember, that's how I'm going to wave to you guys at the opening ceremonies in Tokyo. So you know it's for you. Right, so what's up with this? How does that work? So I have three different things here. What does each represent for this particular right hand with a charged particle flying through an electric field? What's your thumb? Maybe a little pickier. Maybe even pickier. Direction of the velocity of what? Almost. All right, I'll give you a hint. On a positive. Yeah. It's the direction of the velocity of a positively charged particle, because what are we going to do if it's a negatively charged particle? Flip it opposite the direction that particle's moving. So you do have to watch that with this one. So let's go back to the positive. So that's the direction of your positively charged particle. Where are your fingers? And if I'm waving at you like this, that means I remembered you don't remember what things are in the right-hand rule. That's the direction of the magnetic field lines. And then what's your palm represent? The direction that you're pushing on something, so that's the direction of that force. So what happens in this one? We'll do this one real quick. Particle that way. Fingers which way? Into the board. So the only way I can hold my thumb that way, my fingers that way, is my palm pushing up. So this guy, as it entered this field, would get deflected upwards. Everyone okay on that? So same thing will happen if we put those charges into a wire. It's just easier if we've got an equation that deals with things that are more convenient for wires, like the current through the wire, how long the piece of the wire is that's in the magnetic field itself. And of course, here's your magnetic field again. We went through how you turn this into this. But again, be a little careful. This is the force on what? That guy there. For this equation. That's the force on the current carrying wire. So if I've got a wire, let's see what we got here. This. And I send a current through it, and I place this in a magnetic field. There can be a force on this wire. That's how strong that force is. Again, we'll have to watch and see what's the orientation between the direction the current's flowing and the direction of the magnetic field. If they aren't lined up perpendicular, we'll have to account for that here. But we can figure out how strong that is. The direction is the same thing that we just did. The only difference is now our charges are in here, and what makes it a little bit easier is we always are going to make the assumption that the current is in the direction of positive charge carriers if it was positive charges that were doing the moving. So if you've got a current going upwards, then that's easy. I just stick my thumb up. That's the direction of the positive charges moving, and then all I need to do is figure out which way is my magnetic field, and I can figure out which way this wire is going to get pushed as that current goes through the wire in that magnetic field. Any questions on that one? Then we found that if you send a current through a wire, a magnetic field is set up around the wire. In fact, ultimately, what's producing magnetic fields are moving charged particles. Well, if current is moving charges, that will make a magnetic field. And we figured out another right-hand rule to tell pretty easily what the magnetic field looked like around a current-carrying wire. So let's say I've got a current in this wire and it's going this direction, upwards. What does the magnetic field look like that's set up around this? Now can I tell pretty quickly? With the right hand. So this right-hand rule, the thumb is in the direction of what? So I'm going to stick my thumb in the direction of the current and then just grab the wire with my right hand. And as I grab it, what do my curling fingers tell me? The direction that those magnetic field lines are going around this wire. So if I've got a current going upwards, I've got a magnetic field that's going around like this. How about the strength of it as it goes out? It gets weaker the further out it is. And there's an equation that'll quantify that. If I take my current carrying wire and I stick it in a loop like this, that's going to make a magnetic field inside the loop, and it's pretty easy to figure out what that field inside the loop is going to be like. If I've got a current going around this way, how do I tell the direction of the magnetic field right here inside the loop? So again, current's going like that. I just grab the loop with my right hand, with my thumb in the direction of the current, and see what my fingers do inside the loop. And in this case, I've got right here in the plane of the loop, I've got a magnetic field that points down. Where that came into play and got kind of interesting is when we went to this equation, which is Faraday's law with Lenz's law tucked in right there, which is really a beautiful equation giving you instructions on how to make electricity. So let's take a step back of what that says. This left-hand side, kind of a little older term, older symbol, stands for EMF. So I'll write a couple things here. Which is, and I'm going to write this because I see people always doing this wrong. It's have electromagnetic force. It's an old term. It's basically electricity. For us, another way to say that is voltage. And even more convenient, we saw from Ohm's law that we can look at voltage in terms of a current going through a resistor. Ultimately, what this is saying over here is a current. How do you make a current? Electricity? Here's how. Here's what you're making. Of course, you're going to send it through something, a wire or some kind of resistor. Here's what you're making. Here's how you can make it. There's your cookbook instructions. So what does all that say? What does this part say that's not covered? That part. In a bunch of words. Here's a nice compact math way to say it, but a bunch of words, what does that say you have to have happen? You have to have what now? A change in what kind of flux? So magnetic flux as time goes on. So you have to have some changing flux. A changing flux in what? Because I could have like a region space here with a changing flux. What does this say? In a loop or loops of some wire, some resistor. So I need some, at least a loop. And this says if I can get that magnetic flux to change in the loop, I'm going to get a current out of that. And some of you who did that lab actually saw that. So how can I change that flux? We actually had 3 different ways to do it. So I could change the area of the loop. I can make my loop bigger or smaller. I could change the orientation between the area and what? What's the other thing? The magnetic. I know, we had a whole spring break. So I can change the strength of the magnetic field in the loop. As long as that strength is in the process of changing, I'll get a current. I could change the area of the loop. As long as the area is in the process of changing, I'll get a current. Or I can even leave these 2 fixed and just change the orientation between those 2. And I'll get a current, as long as that orientation is in the process of changing. So in all our cookbook instructions, it even says I've got 3 different ways to make this happen. As long as any of these are in the process of changing with time in a loop, I'm going to get a current out of that, out of electricity. And again, some of you went through that lab and got a chance to play with that and see that a little bit. So what's this part indicate?
Just multiplying the whole thing by -1.
No, it means a whole lot more than that. Actually, that little piece there says, in a very compact way, a whole lot of words. There's how you can make electricity. There's how you make a current. What's up with the negative?
More specifically, the direction.
Tells you the direction of that current in that loop or loops. So let's try one here.
Doesn't that mean that it's going in the opposite direction?
I wouldn't quite say it in those words. So again, it takes lots of words to say that one little piece. That says that for you to get a current, let's say this is my loop, this is a little bit easier to handle. Say this is my conducting loop. Somehow I get a change in magnetic flux in this loop, one of these ways. While that is changing, while that flux is changing, I will get a current in this loop. That part is Lenz's law, says that the direction of the current I induce will be set up to oppose the change in the flux that I'm making here to make that current. So lots of words. So let's try one. If this is a magnet, and we'll say this is the north arrow here. So that's the North Pole. I've got a conducting loop like this, and all I'm going to do is hang on to this loop, take this magnet, again the purple cap will say that's the North Pole, and go like this. while this is moving closer to that loop, I will get a current in the loop. Why am I getting a current in the loop? Which one of these have I just changed? I am making the strength of the magnetic field in here stronger and stronger because this pole is getting closer and closer. And we saw that that magnetic field was stronger the closer to that pole if this is a bar magnet, right? Everyone okay there? So if I do this, what's the direction of the current in this loop? Let's look across the top here. Is it coming out towards you or coming back towards me? That's what this part says. So let's see what that means and how, here's kind of a good way to do it. Let's see what our situation is. I've got a flux that's that way. How did I know it's that way? How do I know the flux is that way through the loop? Because field lines, magnetic field lines go out of North Pole. So if this was the North Pole, my field lines would be coming out that way, going through the loop. As I put that magnet closer and closer, so there's what the flux I've got. Is my flux getting weaker or stronger? Stronger. How do I oppose that? Keeping in mind that current adds flux. So I can't like subtract flux. So if I've got flux this way and it's getting stronger and stronger, how am I going to oppose that change with my current? I need to make a flux which way? I need a flux that way with my current. That'll oppose this. So how do I get a current, or what current does that? I have to stick my fingers this way. That's what I want my current to do. And then grab hold of my loop, and that's going to say the current will be that direction. That's how I will oppose that one. Let's try one more real quick. Let's try this one. So I've got this set up. So here's a little resistor here just to let me see if I've got current or not. So maybe a little light bulb goes on if I have current, or something measures it there. Maybe that's a galvanometer or something like that. So I can see what I've got. Here's some conducting wires. Here's a conducting bar. And what this bar is going to do is be able to slide back and forth on these wires, or maybe these are some conducting rails. So I can slide this back and forth. And let's place this in a magnetic field. I'll immerse it in the field. And then let's slide this bar this way. While that bar is sliding, I will get a current in that loop. Why are we getting a current in the loop as that bar slides? We're changing the area of the loop, making the loop smaller. And while the change is going on, we'll get a current in there. So now the question is, what's the direction of the current? It's going to be clockwise or counterclockwise around there. So what's our situation? Flux is which way? That way. Increasing or decreasing? Based on what we did. Notice I'm not changing the magnetic field this time, but it's the flux changing or decreasing. And again, what's an easy way to think of that? It's the field lines. Am I getting more or less field lines in the loop based on what I'm doing? Less. I'm making the area smaller. So I go like this, I'm getting fewer and fewer of those field lines. So I've got flux this way. My flux is getting less and less. How do I oppose that change? I need more and more that way. What kind of current gives me more and more that way? Stick my fingers in the loop the way I need my opposing flux. Grab it with my right hand, and that's going to go around this way. So I'll get a current like that. That all make sense? Starting to remember that stuff? Touch on one more thing that we dealt with, and that's, we looked at a whole bunch of different examples and devices and things like that. I just want to touch on one of them. And these pens actually work really well on a new board. Actually, they're drawn pretty well. Say I make a little thing like this out of iron. Put some loops of wire like that, put some loops of wire like this. And I send an alternating current in this way. So, what does this thing do? How does this thing do it? See if we can walk through what's happening and what the function of this is. By the way, what is this thing? It starts with a T. Yeah, it's a transformer. And what do transformers do? Just simple transformers. These kind of transformers, I should say. Yeah, they can change your voltage as they go in and out, so we can either step up the voltage or step down the voltage. Is this a step up or step down transformer? And how can you tell really easily? Or did you go, well, I got 50.
Play the odds.
Yeah, play the odds and say it with confidence. And is that a step up or step down? If this is our incoming side. Step up. It's really easy to tell, just look at the number of loops. If I go from less to more, I'm stepping up my voltage. If it was the other way around, if I went from more to less, I'm stepping down voltage. So how does that work? Because notice these two wires are not connected. It's not like I'm directly sending current from my incoming wire to my outgoing wire. So how does that, how by sending current in, do I get a current out the other side? And part of that question is, how come this has to be an alternating current? And again, we looked at a few other examples related to this, so I want to just jump right to this one. It's kind of related to the jumping ring, to how your credit card works, but let's talk about this one. So I send a current in here into some loops of wire. Actually, let me use this while I got it. I send some current into a whole bunch of loops of wire. What does that set up inside those loops? I get a magnetic field set up in there. And the direction of the magnetic field depends on if that current went this way or this way in those loops. So for now, let's say the current gets set up, you know, just use some different props here. Say here's my stack of loops. My current is set up so I've got a magnetic field that way at this point. So yeah, I send a current in here, I get a magnetic field set up in there, let's say it points like that. What does this part do? Which is also what these coat hangers did. That can direct those field lines. So rather than a straight solenoid where your field lines come out like that at the top, I can get those field lines to get directed over to the other loops. So now I've got a magnetic field in some loops of wire. If that magnetic field is changing in these loops, then what do I get in those loops? A current out the other side. So why do I need AC current?
Keep changing.
Because to induce that current on this side, remember I need a change in flux, not just a flux, but a change in flux. If I'm continually changing this current, I'm continually changing the strength and direction of this magnetic field I set up that's being put over here, which means I'm continually changing the strength and direction of the magnetic field here, which means I'm continuing to induce a current. So I'll get an AC current in, I'll actually get an AC current out. But by changing the number of loops, I can actually change the voltage. Speaking of, how do I make an AC current? some of you got a chance to play with this. And for those that didn't, let's try and get that today. How do you make an AC current? Let's say I want to make this current here that's going to go into there. Again, there are a variety of ways. We talked about a few examples, but if we're talking about like a power station, it's going to make the current coming out of your walls. What's a nice, easy way to do that? With a loop of wire, stick in a magnetic field, and do what to it? Spin it. And again, we talked about how that would work and why you end up with a current that alternates back and forth, one way the other way, one way the other way. Then it's just a matter of figuring out different ways to spin loops of wire. Do you want a waterfall to spin them? Do you want steam to spin them? If you want steam to do it, are you going to heat it up with coal? Are you going to heat it up with nuclear reactions? Do you want a windmill to spin it? So most of those ways you're seeing power generator just spinning loops of wire in magnetic fields. So any questions there? Okay, so that should get us caught back up from where we were before we took the break.